Going on now in Chapter 2 to Topic 6, Rational Functions and their Graph. Looking at the objectives, we see we're going to find the domain of rational functions, use arrow notation, identify the vertical asymptotes, identify horizontal asymptotes, use transformation to graph rational functions. Then graph a rational function, identify slant asymptotes, and then do a word problem involving rational functions. Now, generally when we think rational functions, we're thinking functions that are in a fractional form. And as we see it here, it's f of x equals a numerator over a denominator. And keeping in mind that you can never have a denominator that equals 0. These are undefined. So when we are finding the domain of something, we have to eliminate those values that make our denominator a 0. And we'll see that as we go on. So as we look at example 1, we see there's a typical rational function, fractional form, where what value of x would make our denominator a 0? Well, you just equate it. X minus 5 equals 0. And then solve it, just transpose it. X, when it equals 5, would make the denominator a 0. So you cannot have a value of 5. So as we look at this notation, domain of our function in set builder notation, it could be x such that x cannot be 5. Now that's one way of doing it. If we were to put this on our number line, we would exclude the 5 by putting a little circle around it, and then solid line going this way, and then a solid line going this way. And we would write that in interval notation as coming from negative infinity, going up to 5, but not including 5, and then in union with the other side, not including 5 again, and going to positive infinity. And that's what they are showing you here. In example 2, again, in rational function, a fraction, what values of x would make our denominator a 0? Well, you could use the square root function where we take the square root of x squared, move this over to the other side and take it square root of 25 plus or minus x would equal plus or minus 5, and that's where they're getting this from. So values of a positive 5 and a negative 5 would have to be excluded. And following what we did earlier, we see that in set builder notation, x is such that it cannot be a negative 5 or a positive 5. And then on the number line, you'd have the negative 5 excluded, the positive 5 excluded, but include all the other values up to that. And let me make a graph of that to show you what it would be like. So again, all of this would be filled in here. This is going to positive infinity on that side, negative infinity on that side. So when we write it, it would be negative infinity up to negative 5 The parenthesis indicates it's not including negative 5. In union now, again, negative 5 is not included, but it's going to go to 5, this 5 here, in union, but we can't include the positive 5 either. The other side of positive 5 to positive infinity. Now, in example 3, as we look at it, what values would make this denominator a 0? Well, if we want to factor that or use that same technique, x squared transposing this positive 25 to the other side is a negative 25. Taking the square root of both sides, we get x is equal to, this is an imaginary number, so it's going to be plus or minus 5i, is what they're showing here. Now, since these are imaginary numbers and are not on the real number line, the domain of our denominator would include all real numbers, because these are imaginary numbers and no real numbers would be excluded. So winding this part up, it's the domain of all real numbers. So an interval notation from negative infinity to positive infinity. Now we're going to look at what is referred to as arrow notation, where we have in this first case x is a plus, x is approaching a from the right, and this next one is x is a to the negative, that is x is approaching a from the left, and a is your value of the graph. And then these are pretty straightforward. X is approaching infinity, that is, it's increasing without bond. And negative infinity here, x approaches negative infinity, that is, it's decreasing without bond. So I'm not sure this chart will be included, but something to put in your notes. So we say a picture's worth 1,000 words. So here we can see pretty much what they were talking about in the previous slide. So here we see A, which is our line here, x equals A, that as it approaches A, this would be A positive here. And where is it going to? Well, out this way is positive infinity. And in this example, again, we have a vertical line A that we'll be defining here shortly, that as it goes away from it, it is decreasing. That's A negative. And where is it going to? It's going to positive infinity. Now in this slide we're also including a very important word, that is the vertical asymptote. Now what is an asymptote? Well, by definition it's a line that something approaches but never reaches. So as we see the curve of this graph, it's approaching this vertical dotted line, which has the definition of x equals a. You recall a vertical line has the official equation of x equals a. So whatever value is on the x-axis, at A, that is the equation of this vertical line, which this dark blue graph never quite reaches, gets closer and closer to it, but never reaches. This is the vertical asymptote. And we see it on this side as well. But here, this is A is increasing, and then here A is decreasing. And before we leave this slide, keep in mind these look like exponential functions. It's a general shape. Now as we go to the next one, again also looking at a vertical asymptote, these look more like logarithmic functions, but again defining it and noticing the value we have here, A positive, and for our domain it's going to negative infinity. And here we see A negative, that is decreasing, and here toward negative infinity. Now your vertical asymptotes are still the same. We haven't described yet how to find them, which is one of the big things we'll be doing shortly. Going on to our next slide, it's nice to have something where we've mentioned it earlier ties in to what we're doing now. Now, whatever value that made our denominator a 0, that happens to be the vertical asymptote. So things we've done already, what were the values for 0? If you recall, one was 5, another was a -5 and a +5. Well, those lines equal to x make your vertical asymptotes. And they'll show us some of this shortly. In example 4 now, they're going to use a different example, but that's okay. X squared minus 1. Again, if we use that technique, x squared equals 1, take the square root of both sides, we get x equals plus or minus 1. So we see it here. So these lines, x equals a -1 and x equals a +1, will make up our vertical asymptotes for this function. Now, if you had a graphing calculator, you could see this very well, but we're going to show you a picture of it here, which is very nice. And there it is. Let's clear this up here. There we go. So if you were to make a graph of this, these were the black lines on the graph are what the curves and lines would look like. And the red lines, dotted, are your vertical asymptote. There is -1 and there is a +1. And again, I would ask you, what is an asymptote? Well, it's a line that something gets close to, but never reaches. Okay, and we've found the domain of those earlier. In example 5, as we look at it, we're asked to find the vertical asymptotes of this function. Well, the graph looks like this, but notice if we take our denominator and equate it to 0, we're going to get x squared equals a -1. And if we take the square root of these two sides, we get x equals plus or minus I. The square root of -1 is I. So that's not a real number. So in this case, where there are no values that make our denominator 0, there is no vertical asymptote. In defining the horizontal asymptote, what would that be? Well, again, a horizontal line has the equation y equals b, where b, you may recall, was our y-intercept. So there is the equation of the horizontal line, which could be the horizontal asymptote of a graph whose function is this. And as we see here, it is approaching our value for b, which is our y-intercept, but would never reach it. And here is, in this case, a is approaching it from the above area, sort of decreasing, but again, never reaching it, the y-intercept, the horizontal asymptote. And here would be a function in which there is, in a sense, an imaginary number. So there would be no horizontal asymptote. In locating the horizontal asymptote now, they're giving us a protocol to follow. It's described here. And we're saying that these values cannot be equal to 0. And looking at the degree of the numerator. So basically, I've tried to simplify this a little. There's our numerator, and whatever the value of n, its degree, its exponent, as compared to the exponent of our value in the denominator, if the n here is less than m, the horizontal asymptote is going to be y equals 0. Now, if the degree, the exponents, are the same degree, the same exponents, then it's just going to be a ratio simplified of the value of that numerator as compared to the denominator. And you'll see an example of this shortly. Now, if n is greater than m, then the graph has no horizontal asymptote. I left some of the writing here so you can see the reference. So here we're going to look at the exponents of this rational function. This is 2, and this is 2. So the degree of our expressions are the same. Well, what did we say? And we look at item 2 here. If the degrees are the same, it's going to be a ratio of whatever values, and let me clear this up a little bit here so we can see it better, is the actual value, which is 9 over 3, which is 3. So our horizontal asymptote here is going to be y equals 3, following the protocol they gave us. And we can actually see that in the next slide. Let me just show that. And again, this function, if you had a graphing calculator, would look like this. And it's a funny kind of thing here. And notice it's not quite touching, although it looks like it might be. This is the horizontal asymptote at 3. All right, let's go on. And looking at example 8 now, we see here our exponent is 1, so that will be the n value. The m value, the degree of this exponent, is 2. So we have that n now, 1, is less than 2. And we said in that condition, our horizontal asymptote, you can see it here, is y equals 0. And let's look at it in a graph here. And we'll clear this part up so you can see it better. So there is our actual x-axis. The equation of that x-axis is y equals 0. And that is, in this case, our horizontal asymptote. Now it's only these far parts here where the lines do not reach it. Going on to example 9, which is our last of the 3 kinds of examples where we're looking at, let me take that away, our n value is 3 here, our m value is 2, so n is greater than m. Therefore, there is no horizontal asymptote in this condition, as it is illustrated in this graph. So we've given you now examples of all 3 conditions. Let's go on. In this slide, we're building vocabulary and looking at some basic reciprocal functions. And here, again, this is our origin. And if we were to graph this, we'd have this curve here, and then this curve here, which in regard to the origin is showing symmetry. And let's just draw the axis of symmetry here, which is right there. And notice what's on this side is symmetrical to what is on that side. If you folded along this axis of symmetry, the red line that I've put there, these graphs overlap one another. Now, what are some of the things that you see here? Well, again, our horizontal asymptote is y equals 0. And there's also a vertical asymptote, x equals 0. And they're describing this as an odd function where both values, if you switch them around, this would be the positive value, this would be negative, this is positive, this is negative. And then looking at this other, where it's instead of x in the denominator, it's x squared, the vertical asymptote is also. Now in example 10, we want to look at transformation of a graph and to this function, this rational function, to this rational function. So there's the graph now of this rational function, this first one. And we've seen the vertical asymptote, horizontal asymptote, and what the graph looks like. Now, let's imagine what happens to this graph if our denominator goes from x here to x plus 2. It's going to shift it, and it's going to shift it horizontally. But is it going to shift it to a positive 2 from earlier lessons or to a negative 2? And if you said a negative 2, that is going to correct. It's going to shift this whole thing over to a negative 2, and our new vertical asymptote will be x equals negative 2, as we'll see shortly. Now, we're also going to move it to a negative 1. Now, here in this position, does it move it up to a positive 1 or down 1? Well, in this case, it's going to move it down 1 to a negative 1 there. So let's see it as we do this, and they have some excellent diagrams here. First, and I'll clear it up so you can see it better, they're moving it to a negative 2. There it is. Our new vertical asymptote will be a negative 2. And now we're going to move it down 1. And then we move it to a negative 1, where our new horizontal asymptote is y equals negative 1. Okay? And notice we also changed the original y-intercept is now a negative 1, 0. And this point here is negative 3, negative 2. So lots of things happening and something to be noted. Here they're going to go through a series of items telling us strategy for graphing a rational function. Number 1, determine whether the graph is showing symmetry to the y-axis, as we've mentioned earlier, or to the origin. Remember, this was the odd and this was the y-axis symmetry. We're also going to find the y-intercept, if there is one, by substituting in the function x as a 0. Going on. We're going to now take a look at continuing. Find the x-intercepts, where if we can, in a sense, find the zeros, where y is 0, what would our values be? Find any vertical asymptote by solving the equation. And again, we've mentioned that what would make our denominator a 0? That would be the vertical asymptote. And then using the strategies, find horizontal asymptote if there is one, using the rules we went over earlier. Number 6, plot at least one point between and beyond each x-intercept and the vertical asymptote. And we'll see this all worked out for us. Gets a little complicated. Item 7, use information obtained previously to graph the function between and beyond the vertical asymptotes. That is, to extend the line. Okay, here it is. Example 11. Graphing a rational function. There it is. So, what value would make our denominator a 0? I think we could all agree it would be a positive 2. So our vertical asymptote would be x equals 2. This is the easy part. Here we're asked to find the y-intercept. Well, remember if x is 0, this becomes a 0, this becomes a 0. We get a -3 over a -2. So this is our y-intercept. And remember, that would be written as 0, 3/2. Now to find the x-intercept, we're going to say y is 0. And when we do that, we get that x is a 1. So there's our x-intercept. And in your notes, you're writing. Now I jumped ahead a little bit earlier and I found the vertical asymptote already, which was x equals 2. Now the horizontal asymptote, since our powers are 1 and 1, they are the same. It will just be the ratio of what's there, and that would be a 3 over 1, which is a 3. So our horizontal asymptote is y equals 3. So in this slide, we're going to start putting in some of the things we know. There's our vertical asymptote, x equals 2. And we did have the x-intercept as 1, 0. So 1, 0 is there. And the y-intercept as 0, 1.5, which is right there. And then we're finding some other points here. And there's a nice chart here to show us some other points that we're going to plot. And there's our horizontal asymptote now of y equals 3. There are some of the other points we're plotting. And again, if we have a graphing calculator, it's wonderful. It shows us this very well. Now I've switched to an online graphing calculator where over here I've put in the function. Remember, I could substitute f of x with a y, and there it comes up. Now notice that here is our, we make a nice line there. This is going to be our vertical asymptote, which is x equals 2, and our y asymptote right here, or I should say our horizontal asymptote, which is y equals 3. Again, if you ever like to see what these are like, this site is desmos.com, and you just ask for the graphing calculator, put in your values over here, and then they give you a nice graph. Okay, a little aside here. Moving on, and I know this one's particularly long and tedious, but lots of stuff. All right, in this case, we're looking for a slant asymptote. So instead of being vertical or horizontal, it'll be on some angle. The graph of a rational function has a slant asymptote if the degree of the numerator, which is this one, is 1 more than the degree of the denominator. So here we had x to the n, x to the m, if this is just 1 degree more than this, you end up with a slant asymptote. And let's look at an example here as we go to our next slide. So looking at the numerator, our degree is 1 more than our denominator, which is just the 1. So how do you find out what it is? Well, we divide this into this. Now you can use synthetic division is what they're using here, or the traditional long division, and you end up with this as an answer. I'm not going to go through that process. We went through that earlier. Now, with this, and we'll clear this up, we then go and say we can leave the fraction part off and say our slant asymptote is this part of our answer. And this is a straight line. Y equals 2x minus 1. So we're going to negative 1, our y-intercept, over 1 up 2, over 1 up 2, and that'll give you this dotted line, which is the slant asymptote. Now remember, we already found our vertical asymptote a number of times by saying it's going to be x equals whatever would make this denominator a 0, which is a positive 2, which they're illustrating there as well. Going on now to our last example, example 14, application. Here we want to find a cost function. Well, cost function is cost of x is equal to, what are the fixed costs of the company? Well, we could put that over here, $500,000. And then the cost to produce each item is 400. And then X is the number of items we're producing. And then it's sort of in slope-intercept form. Y equals mx plus b. Here they're switching it around. That's okay. This way is okay too. In this form, though, we can see this is our y-intercept, and this is our slope. You can see it that way too. All right, let's go on. Now, in this next slide, they're asking us to find the average cost, and we're saying normally it's x bar is the average. They're using c bar as the average. And how many items are you producing? Well, you're producing x items. So you just divide this by x. So this is the formula for the average cost. Now, as you produce various items, and say you're going to produce, let's say, 1,000 of these chairs. So you substitute 1,000 into the formula, and you get $900 to produce 1,000 wheelchairs. Well, how about if you're going to produce now 10,000 wheelchairs? As this number gets bigger and your denominator becomes bigger, notice what's happening to the cost of the average cost of a wheelchair. It's gone down now from 900 to 450. Okay. And if you've got now 100,000 wheelchairs, the cost is $405. Now, as we wind this up, they're asking us to find the horizontal asymptote for the average cost function. Well, again, it costs $400 to produce a chair. So as you keep producing more and more chairs, it's going to get closer and closer to the 400, which is your horizontal asymptote. So in winding this up, our last slide is the horizontal asymptote for this function is this, and describe what that represents for the company. That the cost per wheelchair approaches 400, which is your horizontal asymptote, as more and more wheelchairs are produced. But we'll never reach this because it costs this much to produce one. All right. And again, what you're trying to do is reduce this overhead fixed cost of $500,000. All right. Well, a long lesson, hopefully useful for you.